Hello, welcome to another problem session. So today we have this problem. So you have two metal discs, um, one positively charged, one negatively charged, and they're facing each other. So they're like facing each other. If you look at cross section, and the disc radius is r, each one of them, and the distance from them is also r. This distance could have been d, some other distance, but if you choose r, then the numbers come out very nicely. Okay, so I choose r, and we're supposed to find potential difference between the positive plate and the negative plate. So this will be a positive difference. Now this question can be asked without anything given. If nothing is given, then you have to do either either this or this. Okay, so for instance, if you're not you may have to find some arbitrary point along this, say at this point, what's the electric field. So electric field will be some electric field from the positive to the negative, and you can just integrate from here to there. So you either electric field is given or somehow you have to find electric field at an arbitrary point from one disk, and then from that you can construct electric field from both the disks. We're not going to do this right now. Or you're given at some arbitrary point. So here is two disks again, and so this one is from a disk to some point, a distance z from this. If this was sigma, what the electric potential will be from one disk. So over here, this is the answer for one disk, right? So suppose this is given to us. Okay, then how do we use this to find the answer for this question? So let's do that. Now the reason we do that is because the charges are distributed on a finite size disks, the electric field path is much more complicated. Okay, you can see that you set up the integral, and then the integral, you do it out, and then you get this answer. Hopefully I did the integral correctly. How about doing this integral, doing this integral turns out to be much harder than if you set up the this integral for potential of one disk. You can do that. Let me assume we know this, and the question is how to use this. So let's see, we know this. So from this, let's look at 2 points, points like P1 and P2. So we want to know, we basically want to know V at P2 minus V at P1. So that's what we want, right? So so at point P2, what are the potential? The potential from this disk and potential from that disk. So this will be V from the negative plate at P2 plus V from the positive plate at P2. Okay, and then I'm going to subtract V from negative plate at P1 plus V at negative place at P1. So that's what we want. So each one of them, how do I figure out? So let's, like this, let's set it up, a coordinate system here. So let's call it the z-axis, and let's call it origin. So just like over here, we have a coordinate system because the formula is set to this coordinate system. So this is the answer. So let's call it V. How I'm going to do V from the negative place at P2. How do I get that? So P2 means P2 here, Z equals to R, right? P2 is Z equals to R, and this is Z equal to 0. So this is, I just set sigma to minus sigma because I'm looking for negative. So this is pi times minus sigma. Hopefully I've done this correctly. I didn't double check or anything. Just let's assume this is correct. You may want to check this answer. And so Z for P2 for we're evaluating is going to be R. So this will be R square plus R square, and this is Z is R, so this is just R. So you can see this answer is minus pi sigma R over 2 pi epsilon naught, and we can just put the minus inside. Then it's 1, this becomes minus, this becomes plus 1 minus square root of 2. It's negative. That's correct. Okay, so we got the P2. And how about we go ahead and find this also, V minus P1. So P1 is Z equal to 0, put Z equal to 0, Z equal to 0. So this just simply turns out to pi minus sigma over 2 pi epsilon naught, and this is 0, that gives me R, and this 0, so this is just R. So this is minus pi sigma R over 2 pi epsilon naught. Okay. You can already see that I can just subtract this with this, and you already have that answer. And then it should be twice that much, right? That's obviously we expect because from the symmetry. But let's carry on the calculation. So from this you have a pi sigma R over 2 epsilon naught, 1 minus square root 2. So I need to work that out. And then this one is minus pi sigma R over 2 epsilon naught, and then we need to work this out. Okay, so for P2, regardless of how you use it, we're going to use this formula. We create a new coordinate system. It's much easier to use a new coordinate system. So let's do this ink. So from this I'm gonna have z-axis pointed this way. So for this z equals to r and z equals to 0. So we get a v with a plus at this is P2 still, and this is P1 is still P2. P2 now is z equal to 0 now. So this is going to be, and pi and sigma is plus, so pi sigma, right? 2 pi epsilon naught. I should have cancelled pi's. And this is equal to 0 just makes it r. Let's call this pi is cancelled out. This pi is cancelled out. Pi is cancelled out. I think this was a copying error. There was a pi here. There's a pi here, so this pi cancelled out. And so this one goes over here. So sigma r over 2 epsilon naught. What goes here? V at plus P1 is pi sigma over 2 pi epsilon naught. Should cancel that out to simplify. Now for this, z is r, so z is r for this, and so when you work it out, it's going to be r square root of 2 minus 1. So this is going to be sigma r over 2 epsilon naught square root of 2 minus 1. Now that we have all the pieces, we can write the answer very readily. So sigma r over 2 epsilon naught. You have a 1 here and 1 here. That's 2 minus square root 2, and this one is a minus 1 minus 1. That's that becomes a let's make sure, because this is going to be very common to make a mistake in the sign here. So this is square root 2 minus 2. So minus 2 minus this is a plus, and this minus, so this whole thing is 2 times as much. These are same, equal to each other. That should be from the symmetry of the problem. And so the answer is going to be sigma r over epsilon naught 2 minus square root of 2, and which is positive, and that's a good check on the answer. So that's the answer. So that's using this. And if this was not nothing was given, this will be the path to go. So you want to know, how did I get this? This is just basically using so in a disk you can have a ring as a dq, ring at a distance r. Dq will be 2 pi r sigma dr. So that's dq, and you have a dq and the direct distance and 4 pi epsilon naught. So that's the integration. That's what this is. R is the direct distance from the ring to that point, and so that's the direct distance r, and this distance is z, and this distance is little r, and that's how this integration comes in. It's very easy to do. This assumes reference is 0 at r equals to infinity. So that's the reference we are using for this formula. This is using point charge formula, right? And we constructing it. Okay, so suppose I was really forced to use this, go through the electric field direction. Then what would I do? And maybe I will just leave it as an exercise. Once you find the electric field, and say this is the electric field, I didn't double check it, but suppose this is the electric field z component. So I need to find net electric field and then integrate, right? So let me clean this place up and then show you how you're gonna. I'm gonna set the problem up, and you can do the integrals and maybe check the answers come out the same. Okay, so here we are going to use this answer. So here is this is the negative plate, this is the positive plate, and so this is z-axis, and so we look at dl vector, which is equal to dz k hat. That's the k hat direction, right? And the electric field here will be in this direction, so this will be E plus, and there will be E minus there. So net electric field will be E plus the z component plus E minus the Z component and K hat. Okay, so we are going to get E dot dl will be E plus Z component, E from the minus Z component dz, and we want to have a minus E dot dl from the negative plate to the positive plate. This will give me V plus minus V minus. So this is what we need to do. So minus plus to these things dz. Now the integration of dz, so that's going to be z equal to 0 to z equals to r, because now I know that this is formal and this is specific to this situation, because I got now the integration variable, I can put the limits. So that's what we're supposed to do. And it's a formula for a disk is given to us like this. Hopefully this is correct. Okay, so I need to read up these guys. So E minus is easy to read because that's the same structure like that. This is here, the Z is over here, and this is the sigma, and the Z axis is that way. So we have E minus of Z. This quantity is easy to read. Let's call this pi cancel out, minus sigma over 2 epsilon naught, and the Z is positive the way it's written down, so positive makes it 1, and so it remains a Z and a square root of r square plus Z square. How about E plus of Z? Now plus is over here, not at the origin. So plus is this is minus sigma, and this is plus sigma is over here, and this distance is r. So you can see that from here to here, this is going to be r minus z, and r minus z is, you know, if we're using the same z, r minus z will be greater than 0. So z is between here and here. The z, when I integrate, is going to be between 0 to r, so it's going to be sigma over 2 epsilon naught. This will be r minus z over r minus z, so z will be that distance, and then minus r minus z over square root of r square plus r minus z square. So this will be 1, so we can just get rid of that because this is positive, so it's not going to flip out and become a minus 1. And then we need to put this in here and integrate and see the answer you got here is the same as this over there. So you can see already a lot more work going down this path. So when you have a continuous charge distribution like this case, you it's just finite. So for continuous charge distribution, if you want potential difference or potential, then it's often easy to do for epsilon naught r. Set this up, or you can do through minus a to b e dot dl. That just gives you vb minus ba. So you go this route, a to b. This route depends on which one is easier to do. In a if it's very easy to get electric field and electric field is not that complicated, then often this is the path to go. Okay, this integration, for instance, if you have a charge distribution that lends itself to Gaussian treatment, Gauss's law treatment, where you can get the electric field very easily, then often you go this route. But this is discretizing and then using this formula is also you should try to explore, see which one is easier to get the answer. Both should give the same answer. I'm going to stop the video now. I think we can do a whole bunch more problems as we I'll do a couple more problems in the static potential difference. So find static. So we're talking about static potential right now. If you haven't subscribed to this channel, please subscribe. You can also check out the this website for more physics bootcamp.org for more problems and more discussion. Happy learning physics. Bye.